Hello and welcome back to the channel. In the previous video, we focused on building intuition for peak current mode control, looking at the modulator structure, the compensator, the latch, and the basic waveforms. In this video, we take the next step. Instead of block diagrams or equations, we will look at the real switching level LTspice simulation of an open loop peak current mode controlled synchronous buck converter. The goal here is not controller tuning and not closed loop design. The goal is to understand what actually happens at the switching level, how the inductor current ramp interacts with the comparator, how PWM is generated cycle by cycle, and what the key waveforms really look like in practice. We will start with a quick overview of the simulation structure, then run the simulation, and finally analyze the most important waveforms. The complete LTspice simulation used in this video is available as a free resource, and in upcoming videos we will close the voltage loop around this same peak current mode modulator. So let's get started. This is the complete LTspice simulation of an open loop peak current mode controlled synchronous buck converter. It is a full switching level model, not an averaged model, and it includes the peak current mode modulator, current sensing, PWM generation, gate driving, and the buck power stage. In this video, we won't go into every component detail. Instead, we will focus on understanding how the system behaves and which signals are important. Let's go through the structure first. The schematic can be divided into two main parts. At the lower part of the schematic, we have the peak current mode modulator, we have the PWM logic and associated timing and gate driver circuitry. On the upper part, we have the synchronous buck power stage itself. We will start with the modulator because this is the heart of the peak current mode control. This block implements the peak current mode modulator. The inductor current is sensed and combined with the artificial ramp internally. The summed signal is then compared against a reference threshold, which can be set here. When the current reaches the programmed peak value, the comparator resets the PWM latch and turns the switch off. This decision is made every switching cycle, which is why peak current mode control is often described as a cycle-by-cycle control method. It is important to emphasize that this is an open loop system. The peak current reference is fixed. There is no voltage feedback loop yet, so the duty cycle is not adjusted based on output voltage. This allows us to isolate and study the behavior of the current mode modulator itself. The PWM logic uses a clock to set the latch at the beginning of each switching cycle. The latch is reset by the current comparator when the peak current is reached. This produces a duty cycle that directly depends on the inductor current ramp. This is fundamentally different from voltage mode control, where duty cycle is determined by a control voltage compared to a sawtooth. Here we have the gate driver logic for the synchronous buck converter. That time is included to prevent cross conduction between the high side and low side switches. For this video, the driver is only shown to confirm correct timing, not to analyze driver behavior. Here on the top side is a standard synchronous buck power stage. Here is the switching node. Here flows the inductor current, and here can be observed the output voltage. This allows us to directly connect the behavior of the modulator to the real electrical waveforms. Several key signals are probed in this simulation. We will focus mainly on the inductor current, the artificial ramp, the PWM signal, and the gate waveforms. These signals tell the complete story of how peak current mode control works in practice. Let's now run the simulation and look at the results. Since this is a switching level simulation, it takes some time to complete, so I will skip ahead once the simulation finishes. The simulation is now complete, and here are the resulting waveforms. To keep the discussion focused, I've selected only the key signals that are relevant for understanding peak current mode operation. We will go through them step by step, starting with the PWM control signal and ending with the power stage response. Let's start with the top waveform, which is the PWM control signal driving the converter. Each switching cycle begins with the PWM signal going high, turning on the high side switch. The width of this pulse is not fixed. Instead, it is determined dynamically on a cycle by cycle basis by the peak current condition. This already highlights a key difference compared to voltage mode control. So the duty cycle is not generated by comparing a control voltage to a sawtooth. In the middle plot, we see the signals involved in the peak current comparison. The blue waveform represents the sensed inductor current signal, and the red line represents the effective peak current reference seen by the comparator. At the beginning of each switching cycle, the switch turns on and the inductor current starts to rise. When the sensed current reaches the effective reference level, the comparator trips and immediately turns the switch off. This event defines the end of the PWM pulse for that switching cycle. There are two common ways to include an artificial ramp in a peak current mode modulator, and the exact implementation depends on the IC or MCU being used. The ramp can either be added to the measured current signal or subtracted from the peak current reference. In this particular simulation, the modulator shown here is implemented such that the artificial ramp is added internally to the measured current signal. The ramp itself is also exposed on a separate node, so we can observe it directly here. However, in the literature, the ramp is very often illustrated as being subtracted from the reference. For that reason, the ramp is shown here by subtracting it from the reference purely for visualization, so its influence on the effective comparator threshold is easy to see. This subtraction does not represent the internal implementation, it is shown only to aid understanding and debugging. In the bottom plot, we see the inductor current and the resulting output voltage. The red waveform represents the inductor current. At this operating point, the converter is working in discontinuous conduction mode. This means the inductor current rises during the on time, falls during the off time, and then reaches zero before the next switching cycle begins. The peak value of the inductor current aligns with the comparator trip point seen in the previous plot, confirming that the turn-off instant is determined directly by the peak current condition. The output voltage is shown mainly to confirm correct converter operation. Since this is an open loop system, the output voltage is not actively regulated. At this stage, we are only interested in verifying correct switching behavior, not voltage accuracy or dynamic performance. What these waveforms clearly show is the essence of the peak current mode control. The duty cycle is not commanded directly. Instead, a peak current reference defines the desired inductor current level for each switching cycle. When the measured inductor current reaches the commanded peak value, the comparator trips and turns the switch off. In this way, the peak current command, not the duty command, determines the PWM pulse width on a cycle by cycle basis. So far, we have been looking at peak current mode operation without any artificial ramp. Now let's briefly look at what changes when an artificial ramp is enabled. In this example, the ramp amplitude is set to zero point 0.2. The inductor current waveform itself does not change. It is still determined by the power stage. What changes is the signal seen by the current comparator. The artificial ramp is combined with the current comparison inside the modulator, which modifies the effective threshold used for the turn-off decision. As a result, the PWM pulse width is now influenced by both the measured inductor current and the ramp signal. The basic cycle by cycle behavior remains the same. The switch still turns off when the effective current signal reaches the commanded peak value. At this stage, the purpose of the ramp is not to change regulation, but to shape the current comparison. Why this is important and when an artificial ramp is required will be discussed in a dedicated video. So to conclude, what we have seen in this video is a complete open loop peak current mode controlled synchronous buck converter operating at the switching level. The key point is that the duty cycle is not generated by a control voltage, but by the inductor current itself. Every switching cycle starts with the switch turned on, and the turn off instant is determined by when the inductor current reaches the programmed peak value. This cycle by cycle behavior is what gives peak current mode control its fast response and intuitive current limiting properties. By keeping the system open loop, we were able to isolate and clearly see how the current ramp, comparator, and PWM logic interact without the complexity of a voltage feedback loop. This open loop model is the foundation for everything that comes next. In the upcoming videos, we will close the voltage loop around the same peak current mode modulator, introduce proper compensation, and analyze stability and transient response. The complete LTspice simulation used in this video is available as a free resource, so you can explore these waveforms yourself. Thanks for watching, and I will see you in the next video.